Hello again. We're almost done with this P chapter, prerequisites. I meant to tell you that a lot of things that we cover in this class and pre-calculus, they seem like kind of one-off topics, like they don't really relate to each other. But there are just these little things that will come up in calculus when you take calculus. And they could trip people up if they haven't seen it before. So if it seems like, when you look back on this class, there are a bunch of topics that are unrelated and you're not sure why we needed to learn that, then that's a big part of it. And this one reminded me of it, rational expressions. This one, you won't see these too much. We come back to them a little bit later in this class. We're going to learn how to graph them. But yeah, you won't see them too much, but you will encounter them in calculus. And then if you've seen them before, it makes it a lot easier to deal with them in calculus. So that's the idea, I think. When everybody says, why do we have to learn this? We're not going to use this in real life. The answer is you might use it in calculus, and that could be used in real life. I guess that's my answer. Anyway, that's neither here nor there. Okay, what is a rational expression? A rational expression is the quotient of two polynomials. And remember, quotient means divide. So it's just going to look like a polynomial, something like x squared minus 3x plus 2 over, I don't know, x cubed plus 4x. Something like that. That would be an example of a rational expression. There's a polynomial in the numerator, there's a polynomial in the denominator, and you can always think of a fraction as a division type of problem. So this fraction bar you can think of as x squared minus 3x plus 2, the numerator, divided by that denominator, yeah, blah, 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 blah. So that's why they say quotient. Where we go? Here we go. Quotient, that means divide. That's one thing that's kind of, seems like it's not on topic today, but that's probably good to point out. Sum means add, difference means subtract. So why is that looking weird? Subtract, product. I mean, I think we've used these words even in the last couple of videos, but it's good to kind of spell it out. Product means multiply, and now we've come to quotient, that means divide. It means the result of dividing, I should say, and sum is the result of adding. Like if I said, what is the sum of 2 and 4? You would say 6. That's the result of me adding those numbers. Difference is the result of subtracting. Product is the result of multiplying. And quotient is the result of dividing. Yeah. So they throw those words around in these books as if everybody knows that. Like you use those words in real life all day. Yeah, of course I know what that means. I use those words all the time. But even if you knew it at one point, it's easy to forget. The set of real numbers for which an algebraic expression is defined is the domain of that expression. Because rational expressions indicate division, and division by 0 is undefined, we must exclude numbers from a rational expression's domain that make the denominator 0. So that's the problem there, is that, with polynomials, like in the previous section, if you just have one polynomial, not like these rational expressions where it's the quotient of two polynomials, but if you just have one polynomial, say this guy down here, just this one, I can replace x with anything I want and no problems will come about. But as soon as I make it a rational expression where I'm introducing division or a denominator, either way, it's possible for that denominator to be 0. And we know that that's a problem. There's two problems in math. And this kind of deals with one of them, and someday we'll see another one in math that math people get scared of. We don't like to see this. It freaks us out. Some people are scared of spiders. Some people are scared of sharks, etc. Math people are scared of these things. One is division by 0. That's a no-no, because no one knows how to do that. It doesn't even make any sense. So we just try to stay away from it. That's going to come up in this section. But other sections, we might see the other thing, imaginary numbers. And those, we won't see those in this section. That would come about if you had a square root of a negative number. Because we'll see in sections coming, or actually we already saw it, huh? Oh no, we will see it. Oh my gosh, I'm losing it. We will see it soon in section 1.4. Section 1.4. Why was I thinking we already did that section? I'm losing it. But this is, yeah, division by 0, we'll see that. Those are both problems because they don't really make any sense. Either of them don't make sense. But we'll be worrying about the first one here, but the second one, don't worry about that guy till later. Okay, so we'll see what to do about that. Because eventually we want to take something like this rational expression and be able to replace x with different numbers and kind of see what happens. Really what we want to do is see what its graph looks like. Back in chapter 3, we're going to do that. If that was a function you're given and someone said, what does its graph look like? We'd like to see what its graph looks like, but we need to figure out what x values can we not put in there. What x values would make that denominator 0? Yeah, and they're asking the same question, but in a different way here. They're saying, find all the numbers that must be excluded from the domain of the rational expression. In other words, I should say disclude. I was going to say find them, but you want to make sure they're not in your answer. Disclude all values. I guess I should put S in parentheses because sometimes it's one value, sometimes it's more than one. Values of X that make the denominator 0. Okay, we need to do that. Let's see here. Okay, now that I think about it, I think I'm going to start with the easier example. I hope you don't mind. I'm going to make this our second example, and then maybe I'll do it. An initial example. Oops. Yeah. Okay. How about make it an easier one, just because there's something complicated about this one. I don't want to introduce it yet. Just want to make sure we understand the topic as it is. How about same question, find all the numbers that must be excluded from the domain of the rational expression, but now a different one. How about like 2x squared minus 5x plus 3 over, how about 5x plus 4, something like that. So that, like we mentioned in the previous slide up there, the numerator being equal to 0, that wouldn't be a problem. It's when the denominator is 0, that's a problem. So really, if I replace x with any number you can think of, it could be a whole number, it could be a negative number, it could be 0, it could be a fraction, a decimal, whatever. The numerator, it doesn't really matter what it is. It's going to work out fine. The problems won't arise until the denominator is 0. So we need to figure out for which value or values, depends on if it's one or more, of x is the denominator, which in this case is 5x plus 4 equal to 0. So we're kind of wondering, when is that going to happen? So that just comes down to, we're going to solve that equation. We kind of set up an equation here. When is 5x plus 4 equal to 0? Well, you can maybe guess the answer or kind of reason it out if you wanted to, but we can just kind of start solving this equation. So that's really what you do to figure out which values to disclude from your answer. Just set the denominator equal to 0 and solve the equation. That's kind of the idea. I'm going to say it's first you set the denominator equal to 0. And then we're going to solve that equation, whatever you get, solve for x, and then disclude those values or that one value from the answer. The values, maybe more than one, maybe one from the domain. That's pretty much the kind of go-to step-by-step thing that we're going to do for these guys. So, okay, back in our denominator, we had 5x plus 4. I'm subtracting 4 from both sides. Now I've got 5x by itself and then negative 4 on the other side. The last step would be just divide by 5, and that should give us the value that's going to make x equal to, or the denominator equal to 0. Divide by 5. All right, now x is by itself. It looks like that's the bad value. We don't want to let x be negative 4/5. Apparently, if I replace x with negative 4/5 in this rational expression, the numerator is going to be some number. I mean, it could be 0, it could be not 0. It doesn't really matter. The numerator is fine. It's the denominator that might misbehave, and I guess that's the value that would make that denominator misbehave, negative 4/5, which kind of looks right, because I think if I replace x with that, I could see this coefficient 5 canceling with this denominator of 5, and then you'd just be left with a negative 4, and that negative 4 and this positive 4 would add up to 0, and that's bad. So our domain would be everything except that value. And then the way you can write it, depending on how they want the answer, you can say the set of all x such that x is not equal to negative 4/5. Yeah, I think that looks good. All right, so now we have that one down. I'm going to do the other example. It's a little more complicated because solving, if I set that denominator of this original example that was up here, if I set that denominator equal to 0, it's going to have to use factoring. And I knew that was a little more complicated, even though we just saw factoring in the previous section. It still might make it a little complicated. Oop, I don't want that to follow me. Let's see, I'm going to erase those. Okay, that looks good. Okay. So let's grab this one. Same kind of thing. But one thing I want to note is, if I should add a little kind of note to those step-by-step procedure up there in the orange writing. if the denominator, why are all the words in math so long? Denominator has degree greater than 1, you have to factor then set each factor equal to 0 in order to solve. To 0 in order to solve. Okay. Because what we end up having is, yeah, if I just follow these steps up here blindly, the first step here is, okay, first we're going to set the denominator equal to 0. Okay, let me do that here. In this case, the denominator is x squared minus 5x minus 14. Now it's not possible to just isolate x, because here he is sitting in this term, x squared, and here he is sitting in this term, 5x. And those can't be combined, so it's not really possible to solve for x the way we did in the previous example. You might already know this, so sorry if this is kind of boring. But the way to do it is I can factor this. Hopefully, if this doesn't factor, we'd probably have to use other methods. But in this class, I think they would make sure it always factors, just because that's what we know how to do. And this, just to review from the previous section, this is a trinomial. We got 3 terms. And when you see a trinomial and you're supposed to factor it, you're going to cross your fingers and hope that the leading coefficient is 1. Otherwise, remember, it's that long method with the x and all that. But I don't need to do that, thankfully, because there's a 1 in front of this x squared. Whew. So I should just be able to put these 2 binomials with the x and an x, and then just ask myself, what 2 numbers multiply to make -14 but add up to -5? Okay, -7 and +2. Or vice versa. It could have been, I should say, it could be x plus 2, x minus 7. As long as you keep the correct sign with the correct, guy, then it should be good. Or either way, I'll give you the right answers. And now, as it says, I want to factor and then set equal to 0. Yeah, set each factor equal to 0, I should say. Sorry, each factor. I'm not so good with the English, okay? I'm sorry. I'm better with the math. Even though English is my first language, believe it or not, I'm still terrible at it. But you know what? Everybody has their strengths. Everybody has their weaknesses. Okay. So I'm going to set, I always have to draw this little barrier because I'm going to mix up the 2 equations. Now that I've factored it, one factor is going to be set equal to 0 and solved. That's the x minus 7. And then x plus 2, he's going to be set equal to 0 and solved. And then, okay. I'm going to solve the left one first, just because that's, that's how we read from left to right. I add 7 to both sides. It looks like 7 is one solution. Now the other factor, I'm going to solve x plus 2 equals 0 by subtracting 2 from both sides. It looks like there are 2 solutions to that equation. It looks like, so that means that if I were to replace x with 7 in the original rational expression here, if I replace all those x's with 7, it would be something, it doesn't really matter in the numerator, over 0, and that's a problem. But also this guy too, if I replace x with -2, all the x's in that rational expression, it doesn't really matter what the numerator is, the denominator is going to be 0 also. So this one, because the denominator was more complicated, there are 2 values that make the denominator 0. And most people don't care too much, but this whole set each factor equal to 0, it uses this thing called the 0 product property. Because it seems almost like I can't spell and talk at the same time. Is that a problem? Yeah, because it almost seems like why am I able to do that? Why can I solve an equation by factoring and setting each factor equal to 0? I guess it's because I don't know why. Reasoning it out helps me. I'll remember this easier later if I understand why. So if I have 3 things adding or subtracting together, like I had here, this orange circle I'm circling, or oval, if I have 3 things adding or subtracting together equaling 0, I can't really say anything about those terms. I don't know if some of them are 0 or some of them are negative or positive. It could be all kinds of combinations of things. But if I was able to write it as a product of 2 things, and I think you usually see it written as A times B, so think about that. If there were 2 things, 2 numbers multiplying together to equal 0, how is that possible? Is there something I could say about those numbers? Well, if 2 numbers multiply to make 0, one of them has to be 0. There's no way. I mean, try to imagine all the scenarios. How could 2 numbers multiply together to make 0, but neither of them is 0? That's not possible. So that's what we're using here. If you have 2 things multiplied together equaling 0, then that means that either the left term of the product is 0 or the right term of the product is 0. So that's what we're using. That's kind of why I guess it behooved us, to use a weird word, to write the sum or the difference of a bunch of terms as the product. Now all of a sudden, this polynomial x squared minus 5x minus 14 is written as a product of two things here. X minus 7 is kind of like your capital A, and x plus 2 is your capital B. Those look more complicated, obviously, than A and B, but it's still two things multiplied together, being 0. That means that one of them has to be 0. Either the left thing is 0 or the right thing is 0. And we covered all our bases. We figured out how could the left factor be equal to 0? Oh, that would happen when x is 7. How could the right factor be 0? That would happen when x is negative 2. So that's the idea behind that. That's why we factor to solve an equation, I guess, if that makes sense. Yeah. So it's complicated. It almost seems, yeah, for some reason for me, if someone tells me why something is the way it is, I'm more likely to remember it. If they just tell me, just do it and don't ask questions, I'm probably going to forget, like laws, even laws in real life. Like when someone says, don't jaywalk, you can't walk across the street. That's not a crosswalk. Well, why? Oh, probably because I'll get hit by a car. Cars might not see me. Okay, that makes sense. I'm going to do it. But if there's like a law that doesn't make sense to me, I might not follow it. I mean, anyway. Don't tell anybody that, okay. Simplifying rational expressions, what do we got? Okay, now that we know how to find out what values, oh, you know what? I found those values in the last example, but I forgot to say what the domain is. Come on. I'm not just solving an equation. I was solving an equation to figure out what's not in the domain. So I don't want those. Actually, what I was looking for is not what I want. It's what I don't want. I'm trying to find the bad values. But now that I know they're 7 and negative 2, I'm going to say I want all the numbers x, just call them x because we don't know what they are, such that x is not equal to 7 and x is not equal to negative 2. Any number of all the infinite numbers in this universe, I'll take them, but not 7 and not negative 2. Otherwise, the denominator of that rational expression should not be 0. Those are supposedly the only two that are going to make it that way. All right, so that's kind of the first thing that you might need to do in math with a rational expression is figure out what the domain is. Now we kind of have that down. Hopefully, if you see examples like that or homework problems, you'll kind of be able to follow along. But another thing they might want you to do is simplify a rational expression. So I'd say before we even talk about it, I'm going to say just think of this as, rational expressions, they look like fractions except with polynomials. So it's very akin or similar to simplifying a fraction. Is it simplifying or reducing, I should say? Not simplifying. We call it simplifying for rational expressions, but it's called reducing for, regular fractions with just numbers, like, let's see, like 4/6 or something. That's not a simplified or reduced fraction because you can divide both numerator and denominator by the same number. If you divide 4 and 6 by 2, you get 2/3. These are equivalent fractions. If you were to have a pizza cut into 6 pieces, why am I going off on a tangent? Already, too late. Something like that. There you go. And I ate 4 of them. 1, 2, 3, 4. That would be the same as if someone just cut it into 3 pieces. Oh, geez. And I ate 2 of them. That's, I didn't draw it very good, but that's the idea. So that's what we're wanting to do with these rational expressions, even though they're obviously more complicated looking. I would like to find an equivalent expression that looks nicer and is simpler, just because it's easier to deal with, I guess, is the idea. So kind of keep that fraction thing in the back of your mind, though. That's what we're going to try to do. But it's definitely more complicated for polynomials. What we're going to have to do is something similar to, instead of dividing like we did with this fraction, try to factor it into primes. Is 4 a prime number? No. 4 can be written as 2 times 2. Those are prime numbers. And 6 is not prime. I can write it as 2 times 3. And then I can cancel any like primes like that. And then whatever remains is what's left. That's kind of be more probably similar to what we'll see with these rational expressions simplifying. We're going to take the numerator, factor it as much as we can, not prime factor because they're not numbers, they're polynomials, but we're going to factor it in the way we saw in the previous section, and same thing with the denominator, and then kind of look around to see if there are any like factors we can cancel. That's what we'll do. So that's pretty much it. It's like in this example, we got x squared minus 1, x squared plus 2x plus 1. First thing we're going to do is factor the numerator and the denominator. And denominator, you know what? I should actually say that's the second step. Thank you for reminding me. I don't know who I'm thinking. The little person that lives in my brain. Let's see. First thing you want to do is find all value, plural, singular, I don't know, values that make the denominator equal to 0 and disclude those from your domain. Make sure that's true. Disclude from the domain. There we go. Okay, and then we're going to factor the numerator and denominator. Then we're going to cancel any like factors if they have them. If they don't have them, then I guess it was already simplified as it was. But if there are any like factors, then we will cancel them. Between numerator. I hope you don't mind I abbreviate. Oh, yeah, denominator. That's it. Yeah, that's pretty much it. Okay, so this one here, yeah, this is even more factoring practice. If you didn't get enough factoring practice, here we go. The numerator is a binomial, x squared minus 1. It has two terms, so it's either, if it factors, it's the difference of squares, difference of cubes, or the sum of cubes. That second power lets me know it's going to be a difference of squares, so that's a good one. Difference of squares. And that one always looks like x plus something, x minus something, or you could switch the plus and the minus if you wanted to. Or sorry, yeah. 1 and 1 are the things that multiply to make 1. So that's what that's going to look like. And then the denominator, thankfully, that's a trinomial with leading coefficient 1. There's nothing in front of x squared, thankfully. So it should be this kind of simple factoring method. I'm just looking for, okay, what numbers multiply to make 1, that last term, and then add up to 2. And like I mentioned in the previous video, I always have to write this multiplication and addition signs, so because I'll forget which one's which. Like, oh wait, do they have to multiply to make 2 and add up to 1, or is it the other way around? Yeah, if I see the plus on the left, I think maybe that means you're a visual learner, huh? I mean, I'm a visual learner. That helps me. Plus on the left, times on the right. Okay, so that helps. All right, what numbers multiply to make 1 but add up to 2? I guess 1 and 1, right? 1 times 1 is 1, which is what we wanted, and 1 plus 1 is 2. All right, that looks good. We did step 2, but I forgot to do step 1. Didn't I just say I'm supposed to find the values that make the denominator 0? And then I just skipped that step just because I don't see, there I am, not following the laws. There are rules in place for a reason, and I just don't follow them. Wow. It's called a rebel, okay? It's pretty, anyway. So I'm going to take the denominator and set it equal to 0 and try to find any values that make that denominator 0. All right, set it equal to 0. Same kind of thing with the previous example we did. I'm going to need to factor that. And thankfully, oh, actually, I already did factor it. Well, that's kind of helpful. There we go. All right, and then now I'm supposed to set each factor equal to 0 like we did in the previous example. But now I'm realizing these are going to give me the same value, right? If I set x plus 1 equal to 0 twice and then solve it, that seems like kind of silly. This is because they were the same factor. I'm going to subtract 1 from both sides. So it looks like -1 is the bad value. Usually if this was a different factor, it wasn't the same exact guy, I would actually solve it, but I don't really need to. So whatever happens, I'm going to make sure that my answer has whatever. Okay, this is how I want to do it. The answer is blah, and then I'm going to put comma, x cannot be equal to -1. All right, so I'm going to, because I will forget to put that, I swear. I'll just reduce the fraction or simplify the rational expression and then just forget to say that, wait, x cannot be whatever. All right, so now I've back to step 2. I factored it. Okay, now we're on step 3. Are there any like factors between the numerator and denominator? So I could not cancel this x plus 1 and this x plus 1. They're both in the denominator. It'd have to be one of them in the denominator, one of them in the numerator. All right, now we got it. The x plus 1s cancel in the numerator and denominator. What's left is, these are not quite the same factor. It looks almost the same. They both got an x, they both got a 1, but the signs are wrong, so they won't cancel. X minus 1 is left on the numerator, x plus 1 is left in the denominator. I don't really need to use the parentheses anymore. They were really only there to separate the factors that were next to each other. And now the numerator and denominator have there's only one factor in each, I guess I should say. So that's my answer, but I need to say that x cannot be equal to -1. Yeah. Because I guess the thing is, in this one, this doesn't apply, but in some problems, once you cancel that like factor, like we did in step 3, I guess it is, we canceled the like factor, you might not see that factor anymore that made the denominator 0, if that makes sense. Here, you could actually identify the values that make the denominator 0, but in the simplified form, you might have lost that information. So you have to find that, make sure you have that first, and then kind of stipulate it later. Okay, that's good. That matches what the answer said here. All right, so that's kind of the idea there. It's pretty much, this whole section is factoring practice. You're going to be factoring a lot. That's what all this is about. If you simplify a rational expression, if you find its domain, if you multiply rational expressions, you divide them, you add them, subtract them. It's all about, yeah, the factoring. So we're going to get really good at factoring with all this practice. Okay, so now we've seen how to simplify it, but what if you had two rational expressions multiplying together? How do you work on that? Like this example here, we're going to look at. This is one rational expression. It's got a polynomial of x plus 3 over x squared minus 4, and then we've got a different one over here, a bigger one. To multiply them, it's very similar. I would say if you ever get stuck on these and you don't remember how to do it, just think about fractions. Like we said, 4, 6, I'm not very good at, I'm not very creative. How about 9/12 or something like that? If I want to multiply those, I could just multiply across, but what I could do is, which is easier, is to simplify it first. I see some reducing. 4 goes in, you know what, actually, sorry. To make it similar to what we're doing, I'm going to actually factor into primes because we can't just cancel stuff with polynomials in the numerator and denominator. I'm going to make 4 is 2 times 2, 6 is 2 times 3, and 9 here, he's 3 times 3. 12 is, if I break it down to primes, 2 times 2 times 3. And now I can kind of go wild with canceling. I see, let's see, vertically these 2's can cancel, diagonally these 2's can cancel, diagonally these 3's can cancel, and vertically, holy moly, a lot of things cancel. Who's left in the numerator? Nothing. But when you have a fraction and everything cancels from the numerator or denominator, it's just an automatic 1 left. The denominator, I almost missed this guy. You didn't get canceled, did you, little guy? You're so cute, little 2. So that's the idea behind what we're going to do with these rational expressions as well. Both numerators, both denominators get factored, and then you can kind of go wild canceling. You can cancel on the diagonal, between one numerator and denominator, or vertically, you can cancel, but you cannot cancel horizontally. You can't cancel a factor that's in the numerator and another numerator, or same thing with denominator. So first thing we do, like we said, is factor all numerators and denominators completely. So make sure that, like we saw in the previous section, sometimes you factor one time, but then one of those factors factors further. So make sure you factor all that you can. And then it says divide numerators and denominators by common factors, or in other words, just cancel common factors. That's just a different way to say it. Cancel common factors between, I want to specify because I don't want it to be between two numerators or two denominators. A numerator and a denominator, because that means you can cancel vertically or diagonally, but not horizontally. And then our last step would be whatever's left over once you've done canceling, multiply the remaining factors in the numerators and multiply the remaining factors in the denominators, which is what we would have done in this example here, but it seemed like everything canceled. But if there were multiple factors left in the numerator, I'd multiply them together to get my numerator, and then the same thing with the denominator. That's what I'm going to do here. I'm going to see just kind of one by one. I guess, again, because we read from left to right and top to bottom, I always just start from the top left and then move from there. So that first numerator, let me look at him. X plus 3, I don't think that can factor. That looks like a factor that came from a more complicated polynomial. So I think that is prime, or it can't factor. It doesn't fit any of our factoring techniques. It's a binomial, so it has 2 terms. But it's not a difference of squares. It's not a difference of cubes because there's no power on x, and there's not a sum of cubes. That's probably about as good as it gets right there. And then the denominator, okay, let me focus on him. Okay, x squared minus 4. That's a binomial, so it's one of those 3 types of techniques I just mentioned. But x is being squared, not cubed, so I'm pretty sure that's a difference of squares. Difference of squares, so I know it goes something with a plus, something with a minus. And then what is being squared to give me that first term, x, so that goes in the first spot for both binomials. And then what's being squared to give me that second term, 2 is what's squared to give you 4. So that's the first rational expression factored. Okay, now I'm going to look at the second rational expression, and it doesn't matter what order you factor these in. If you think you want to go from the easiest looking one to the hardest looking one, or try to tackle the most difficult one first, it's up to you. But the numerator of the second or rightmost rational expression, thankfully that's one of those trinomials that factors easily because it has a 1 in front of it. That's what I call it. I don't think books call it that. I just call it easy trinomial method. Anything seems easy compared to that difficult one with the x and all that. I feel sick when I think about it. It's terrible. All right, I want to know what numbers multiply to make -6 but add up to -1. Okay, I think I know. -3 and +2, or vice versa. +2 on the left, -3 on the right. Yeah, I think that would work, right? I do a quick check. -3 times 2 is -6. Okay, yes. And -3 plus 2 is -1. Yes, yes. Check, check. Okay, one more thing to do, and then we can go wild. This is the fun part after that. All right, we're not gonna cancel. We're gonna factor that last denominator there. We got x squared plus 6x plus 9. That's a trinomial. Again, luckily that leading coefficient is 1, so it's going to be pretty simple. I need to figure out what multiplies to make 9 but adds up to 6. I think just 3 and 3, huh? Because 3 times 3 is 9, 3 plus 3 is 6. There we go. Okay, now this is the fun part. I get to look around and see what's alike between any numerator and any denominator. It doesn't matter what order you do it in. The first one I saw was this x plus 3 and this x plus 3. They're the same, so they cancel. How about what's left? I see across the other way, x plus 2 and this x plus 2 cancel. And I think that's about it. And kind of like the previous problem or before I mentioned, this x minus 3 and this x plus 3, they almost look the same, but the sign changes makes them a different factor. So I think we can't do anything with that. Let me see. And then I got to make sure I don't miss any factors that were not canceled. I think in the numerator, the only factor that didn't get canceled is that x minus 3. So he would just be all by himself up there in the numerator. In the denominator, though, there's, let's see, 2 factors. Oh, whoops. We got the x minus 2 over here and this x plus 3. So I could just write them next to each other. It kind of depends how they ask you to write your answer. But I think right here, this being factored, it's only helpful if x minus 2, x plus 3, the denominator is factored, if we have a hope of reducing. But now we've already reduced as much as we can. So a lot of times I think you'll see them multiply it back out. X times x is x squared. X times 3 is 3x. -2 times x is -2x. And then lastly, -2 times 3 is -6. Real quick, I got some like terms. Let me just simplify that real quick here. X minus 3 over x squared. And then these two terms add up to just 1x or x, and then -6. There we go. So even though this is correct, I would definitely be happy with this on the midterm. If this was a midterm problem and you left it like that, I would not mark you down any points. But the homework's very picky, so they might say, and they might prefer the multiplied out version. I don't know why. If you're ever not sure how to write your answer for the homework, just think, what's the most work I could have to do? That's probably what they want. Like, why is this not? I don't know why it looks nicer to me, but whatever. I guess they want you to do more work. It makes them happy. Some people are just like that, right? They get joy from other people not having a good time. Anyway. That was fun, right? Oh, I guess I left another slide in case we didn't do it all in one slide, but so feel free to leave this slide empty because, yeah, but if you needed more room, then there's more room. But depends how big you write. All right, now we learned how to multiply. Multiplying rational expressions is just similar to multiplying fractions. Let's see. We got the quotient of 2, but now dividing. We want to learn how to divide. It's a little bit, before we even talk about it, let me talk about with fractions. If it was, I better think of a new example. 2/9 divided by, let's see, about 8 over 15, something like that. If someone says divide, okay, I can't reduce yet. I have to flip and multiply, if you remember from way back when. I take the first fraction, rewrite it the same, change the division to multiplication, and then flip the second fraction or the rightmost fraction upside down. That one was at 8/15, now it's 15/8. And now it's just like the last problem, because now it's multiplication. The last example, I would just, once I flip and multiply, I can rewrite it, and I'm going to prime factor it. 2 is the first numerator. He can't be factored. It's already prime. But 9 is not prime. He can be written as 3 times 3. And then this numerator is 15. That can be written as 3 times 5. The denominator of 8, that's 3 2s. 2 times 2 times 2. All right, now we can go wild with the canceling, if there is canceling to be had here. I think across the diagonal, I see some 2s can cancel. Across this diagonal, I see some 3s can cancel, but that's about it. So I'm just going to multiply what's left. In the numerator, there's only a 5 left, so that would be it there. The denominator has 3 factors, though. 3, 2, and 2. What's 3 times 2 times 2? I think 12. So that's very similar to what we're going to do here with the dividing rational expressions. We pretty much change the division to a multiplication problem and then proceed as we did in the previous example. The quotient of two rational expressions is the product of the first expression and the multiplicative inverse or reciprocal of the second expression. That's what they call this guy. If someone says, what is the reciprocal of, or the multiplicative inverse of this guy? 8/15, you just flip it upside down. That's what we call the reciprocal. So if I stand upside down, or I'm doing a handstand, I'm the reciprocal of myself. Boom. That doesn't make any sense. Okay, the reciprocal is found by interchanging the numerator and the denominator. Kind of like if I'm doing a handstand, I interchange my feet and my head, I guess. They switch places. Thus, we find the quotient of two rational expressions by inverting the divisor and multiplying. Yeah, and then no need to even describe what to do next because it becomes a problem that was just like example 3. All right. So now let's start doing this. Let's think about what we do first here. So before I do anything, I really want to right now factor and cancel factors, but I can't cancel factors until I flip and multiply. So that would be my first thing. Make sure this is a technical terminology, but that helps me to remember because it's such a short thing to say. Flip and multiply. Okay. So keep the first fraction exactly the same, or the first rational expression. Sorry, I'm saying the wrong thing. Multiplied by. Now flip this guy upside down and change division to multiplication. All right. The denominator was 3x squared plus 3. I factor him out. Bring him to the top, and then the old numerator is going to go to the denominator. Did I say that right? There we go. And definitely do not do like I've seen many students do when they forget how to do these problems. You can't cancel individual terms. So for example, I see this x squared in the numerator and that x squared in the denominator. They can't cancel. You can only cancel them once they're written as a product. That's why we factor. Because of the zero product property kind of thing. If I see something that looks like a times b over a times c or something like that, that's like me writing, a fraction 2 times 3 over 2 times 5, then they can cancel. But you couldn't say 2 plus 3 over 2 plus 5. Oh, the 2's cancel. That's not true because on one hand, what's 2 plus 3 in the numerator? That's 5. 2 plus 5 in the denominator is 7. Is that the same as if I canceled those 2's and I got 3/5? Those are not the same fraction. This is bigger than this. So that's the reasoning behind why we have to factor before we try to cancel. Nothing cancels within fractions or rational expressions until we have multiplication. If it's just addition and subtraction, nothing can cancel. A factor all. I'm just going to say factor all. Makes it sound better, cooler. And then we're going to cancel like in example 3, I think that was. Yeah, now we're back to just exactly the same thing we were doing in example 3. We got the numerator in the left rational expression. We got, okay, it's a trinomial with leading coefficient 1. So I got two numbers that multiply to 1 but add up to -2. I think I got -1 and -1 because -1 times -1 is +1, and then -1 plus -1 is -2. Yep. Now this denominator, it's almost like misleading because there's two terms, x cubed plus x, and then the only 3 techniques I know for 2 terms is difference of squares, but that's not a difference because it doesn't have a minus. It's not that. It's not difference of cubes because it's not a minus. The only thing it could be is sum of cubes, but the second term, I don't think that's anything cubed. So what it actually is greatest common factor. That's something everybody forgets about. That's the only factoring technique I can use because the 2 terms between x cubed plus x that they have in common is x. And if I factor that out, x squared plus 1 is left. But yeah, you can always check by distributing that x back in. And I might think for a second that what's left, x squared plus 1, can be factored further, but that's not a difference of squares because of the plus. That's a sum of squares. And that can't be factored. We said in the previous video that that's prime. Okay. Now this numerator, I'm going to factor, let's see, same kind of thing. It doesn't really fit any bills. If it fit the bill of any of the factoring techniques, I'm just going to factor a 3 out because they have that common factor. And similarly, that's the sum of squares, which can't be factored. Now we're going to look at the denominator. That's another trinomial with leading coefficient 1. And then I want to find out what are the numbers that multiply to -2 but add up to 1, 2 and -1, or vice versa, -1 and 2. I think that'll work. Okay, now I think I've factored everything as much as I can. I'm gonna cancel some like factors. I got the first one along the diagonal I see is this x minus 1 and this x minus 1. What else? Oh, this x squared plus 1 and this x squared plus 1 happen to be the same, but I think that's about it. Vertically and diagonally, I don't think I can cancel anything else. Looks good to me. I'm gonna just multiply across now. I got x minus, it kind of helps me to write what's left next to each other. X minus 1 here and the 3 from here. I could put it on the left if I wanted to, I don't know. And then on the denominator, x is left from that guy and x plus 2 is left from that guy. And I'm okay if you left it like that on the midterm, but I think in the homework, they're going to want you to distribute it. 3 times x, 3 times -1, and then distribute this x in here, x times x times 2. There we go. And that's it. So it seems like a lot of work, but I think the bulk of the work is factoring. The better you get at factoring, the faster a lot of the problems will be in this whole thing. Let's see. Oh, and I left more room. I could have saved myself some room, but nope. I like to just squeeze everything in there. Okay, now we're going to talk about adding and subtracting rational expressions. This is a lot more work, but again, if you ever get stuck, think about regular fractions and you'll kind of hopefully remember what to do. So the first example that we'll do, they have the same denominator, these rational expressions. So it'll be very similar to fractions that have the same denominator, like 5/9 take away 2/9, something like that. It's very similar. So what you do, if they have the same denominator, you're able to add or subtract them. But what you do is just add or subtract the numerators, right? 5 minus 2 would be 3, but the denominator stays the same. You don't change that. And then you can reduce if possible. So either just do the subtraction or addition of the numerators and then keep the denominator the same. And then you can reduce like that. 3/9 becomes 1/3. So it'll be very similar. To add or subtract rational expressions with the same denominator, we first add or subtract the numerators, just whatever the sign is between them, do subtraction or addition. And then we place this result over that common denominator, just keep it the same. And then simplify if possible, like we did. We knew that 3/9 reduced. And then check for excluded values. All right. So we gotta, okay. Subtract these guys. Let's see. I should check, even though they said these will have the same denominator, I should check. Do these have the same denominator? Yes, okay. Same denominator. So we're good to go. In the next example, we'll see what to do when they're not the same denominator. All right. So this really helps me because it's kind of tricky, especially with subtraction. This subtraction sign is for everybody in this numerator. So you really do need to distribute it onto everyone. It's not just going to be the 3x gets the minus, it's going to be the 2 as well. So for me, just to make sure I don't make a mistake, every single time I do this, I write the first numerator and then the sign between whatever it's a plus or a minus, and then the second denominator, or sorry, the second numerator in parentheses all over the same denominator. So I have combined them into one fraction, but I haven't simplified it yet. And like I said, I only do that because I'm pretty sure that I'll forget to distribute this minus sign onto the second term. And if there's a third term, even in the second numerator, that would be hard. So I would say, especially if you don't feel too comfortable with this material, I would make sure I do that every time just to make sure. Okay, because they would give you the wrong answer if you did it the other way. If I give that subtraction sign to the 3x, that's what it looks like. And then also the 2 should get the subtraction sign. And the denominator is already simplified, nothing to do there. Now the numerator, there are 2 like terms. I can combine those. X minus 3x is -2x. And then I've got the -2. That was kind of the odd man out, no like term for him. And then of course over the denominator. Okay, now I can try to simplify it. Simplify, just like the very first example we did, actually the second example. The first example we did was finding the domain, but now we want to simplify. I would see if either the numerator or the denominator can factor. The denominator is just as simple as it can get, it's prime. But the numerator, I can factor a -2 out. Both terms have a -2 in common. And then I ask myself, okay, -2 times what would be -2x? I would need an x in there. And -2 times what would make -2? It'd have to be a 1. And then I say, wait a second, look at that. x plus 1 cancels. What? And then if, like we saw with that just regular fraction example, if you cancel everything from the numerator or everything from the denominator, like is happening here in the denominator, you're automatically left with a 1. So there's a -2 left in the numerator and a 1 left in the denominator. And that actually is just -2. Any fraction with a denominator of 1 can be simplified to a whole number. So it's crazy, but these two rational expressions subtract to make just -2. Doesn't matter what x is. X could be anything it wants, but you will get -2. But it did say, remember to disclude any values that would make the denominator 0. So I should think of that. What is the domain question mark? I'm going to take the denominator. They have the same denominator, so it's don't have to worry about which one am I looking at. They're the same. I'm just going to set it equal to 0 and solve. So that's the one I don't want. That's what I should say, is that that guy is discluded. The answer, that subtraction problem comes down to -2. That is if, oops, x does not equal -1. If x is equal to -1, that subtraction problem is undefined. It doesn't even make any sense. But otherwise, as long as x is not -1, it should be equal to -2. That's kind of crazy. I'm sure they designed this problem that way. Whoever came up with this example, they said, let's make sure it comes down to a nice number to freak everyone out. Because we know that, I know I would freak out if I saw, wait, the problem had a bunch of x's in it. My answer doesn't have any x's in it? That can't be right. But I think they just designed it that way. That would probably happen very rarely in our future. I just want it, yeah. Anyway, okay, first one. Now we want to be able to find the least common denominator. Yeah, what if we were given two fractions and they wanted us to add or subtract them, but their denominators were not the same? That would be a bummer. Okay, what would we do? Oh, Lord, factor each denominator completely. Then we need to list the factors of the first denominator. All right, this is sounding crazy. Let me make it similar to an actual fraction problem. Like if you were taking, how about 4/5, and I want to subtract, I don't know, something 12ths or some crap like, I mean, stuff, no, not 12ths. How about, you know what? Forget that. I'm going to do a different one. Sorry. 7/10. Let's get crazy over here. Subtract, wait for it. Something nuts. How about something 1/4? There you go. All right. How would we do that? The good thing about these rational expressions is they behave very similarly to fractions, but it's like on a totally new level. Yeah. Like so, yeah, anyway. What would we do? We need to figure out what the common denominator is and make sure they both have that denominator. Common denominator. With fractions, I think if you're familiar with them, it might be easy for you to come up with that common denominator, but with these rational expressions, it'll be more difficult. So what we'll do with the rational expressions is factor each one. So for example, the first denominator is 10, the second denominator is 4. I'm going to factor them into primes, okay. 10 is 2 times 5, 4 is 2 times 2. So that's what they look like. And I need to, let's see, between the two, I'm going to actually write this as 2 to the second power. I need to grab my common denominator. Common denominator will contain any primes between them. Between this prime factorization of this denominator and this guy, all I see are 2s and 5s. There's maybe more than 1 2, maybe not, but yeah, there we go. So but then you take the largest number of 2s you see. So between them, I see this, the first factorization has 1 2 only. The second factorization has 2 2s. I want to be greedy and take as many as I can. Take 2. And then as far as the 5s go, who has more 5s? The first factorization or the second one? The first one has 1 5. This has no 5. So I can't take more than 1. That's the highest I see. So that would be the common denominator. 2 squared is 4 times 5 is 20. So you probably already knew that looking at these, that their common denominator would be 20. And so that's fine, but with rational expressions, that's kind of what we're gonna have to do because they're more complicated. Is factor everybody, grab the factors you see, take as many, the most that you see, and then blah, blah, blah. Excuse me, and then we kind of give each fraction what it needs to get there. So the first fraction is 7/10, but I'm gonna just real quick rewrite it as 10 is 2 times 5. So 2 times 5, what is he missing that this common denominator has? 2 times 5 or 10 only has 1 2. He needs to get 1 more to get there. I need to give you 1 more 2, my friend. But whatever you do to the numerator, you have to also, or sorry, whatever you do to the denominator, you have to also do to the numerator. So I'll multiply that guy by 2, and maybe I'll just kind of stick with that guy until he looks good, and then I'll move on. 7 times 2 in the numerator will be 14. The denominator, 2 times 5 times 2 is 20. That's how I designed it. Of course, try to hold back from reducing that. When I see 14/20ths, I say, oh, that reduces. I want to reduce it. But you did that on purpose. You don't want to go back to where you were here, 7/10, because then I can't add or subtract. So it is very tempting to, to reduce. And then the second fraction was 1/4, but I want to write 4 as 2 times 2. That denominator already has the 2 squared or 2 2's from the common denominator over here, but what is he missing? He's missing this 5. I need to give him a 5, but whatever I do to the denominator, I have to also do to the numerator. The numerator becomes 1 times 5, okay, which is 5. That's not so bad. And then the denominator, 2 times 2 times 5 is 20. That's how I designed it. Now I can go ahead and subtract. 14 minus 5 is 9 over the common denominator of 20. That doesn't reduce, so I'm done. That's the idea behind these guys. This is probably as complicated as this section gets when you're adding or subtracting rational expressions that do not have the same denominator. Oh my gosh, that's where I get nuts. But again, it's all about factoring. I think if you're good at factoring and you're careful, they should be fine. And if you're not good at factoring, all the factoring you're doing in this section will probably give you enough practice to become good at factoring. That's the good news. Oh, here we go. So these steps here are just gonna describe what we just did. Find the LCD of the rational expressions. That's kind of what we did off to the side. They were regular fractions, but yeah. All right. Second step is rewrite each rational expression as an equivalent expression whose denominator is the LCD. Like we did, we have to multiply the numerator and the denominator of each rational expression by any factor or factors needed to convert the denominator to the LCD. Kind of like we said, the denominator is this. If I want it to look like this, what is it missing? That's what I need to multiply it by. Once you do that, add or subtract numerators, whatever the sign between the two rational expressions is, placing the resulting expression over the LCD. If possible, simplify the resulting rational expression. So let's try it. This is probably as hard as it gets. So you just, as long as you're careful, you're good to go. Yeah, resist the urge to do what I've seen a lot of students do. If they come to the midterm and this problem's on there, they say, oh crap, I don't remember how to do this. They'll just like combine like terms, you know, they say, oh, x minus x is blah. I got a 10x and a 2x subtracting. You cannot subtract these unless they have the same denominator. So that's not going to work. Or they'll start reducing. They'll say, this x and this x cancel, this x and this x cancel. 4 reduces with 10 to make 2. Oh my God, no, no. You can't do that. I wish, oh my gosh, please, believe me, I wish we could do that. That would be so awesome. Our lives would be so much easier if math worked like that. Oh, Lord. But anyway, we got to do it the hard way. Let's see. I'm going to find the LCD, least common denominator. It'll probably help to factor the denominators. Let's see. The leftmost denominator is just kind of an easy factoring method. It's a trinomial. Luckily, leading coefficient 1. Let's see. I want to find two numbers that multiply to make 25, but add up to -10. That would be -5 and -5, right? Yeah. Okay. And then I'll subtract. The numerator here looks good. Now denominator, that is a binomial, but it doesn't fit the bill of difference of squares, sum of cubes, difference of cubes. All I can do there is factor a 2 out. If I factor 2 out, x minus 5 is left. All right. So between those two denominators, my LCD will have, what I do is I'll just grab everything I see between the denominators. What do I see? I see some x minus 5s. I'm going to think about how many I need. And I see a 2. So I definitely need some number of 2s and some number of x minus 5s. I only see 1, 2 on the rightmost fraction and no 2s on the leftmost fraction. So I only need 1. Between these guys, I see 2 x minus 5s. And here I see 1. I'm greedy when I get my LCD. I want 2. You need to take any factor you see and also the most you see. That would be it. Okay. So there's my LCD. It's 2 times x minus 5 squared, or in other words, x minus 5 twice. There we go. All right. So I look at, and then each individually, I look at those fractions and I say, for example, this left fraction, x minus 5, what's that denominator missing that I see here? I'm going to kind of look between the two. What am I, when I say I mean this denominator missing from the LCD over there. It would be the 2. I have both x minus 5s, but I'm missing the 2. So I'm going to multiply top and bottom by 2. And then kind of similarly for this fraction, what is that denominator missing from the LCD? What am I? You don't have to write this out, of course. This is kind of happening in your head. Missing from the LCD. This denominator here, he has a 1, 2, and he has 1 x minus 5. He needs one more x minus 5 to get to where he wants to be. This is his idol. He wants to be just like this guy. Isn't he so cool? 2 x minus 5, x minus 5. I want to be just like him someday. So, well, then you need another x minus 5, dude. You do it. Just do it. All right, I think that looks good. Now it looks like a mess, but let me see what's going on. This numerator now, it was just an x, but now it's an x times 2. But I could just write that as 2x. I don't need to get cute and write x2. It's 2x. Come on. And then this denominator that on the left fraction, I'm going to put the 2 in the front also. 2 times x minus 5. And you could write the x minus 5 separately as it is, but I'm lazy and I just want to write the square instead. Okay, subtract, because there was a subtraction sign. And then the second numerator, it had an x minus 4, but I gave it an x minus 5. Now, previously, the x minus 4 didn't need parentheses around him because there was nothing for him to multiply by. He was all by himself, you know, like when you're at home, you feel like you don't have to wear pants. You just walk around, whatever. And then all of a sudden a guest comes over and says, oh crap, I got to put pants on, you know, stuff like that. And there's x minus 5 coming over. So, okay, the x minus 4 is like, all right, I guess I need parentheses now, geez. Trying to relax at home, and here comes somebody, didn't even invite you over. And then the denominator was, I got a 2, and then x minus 5, x minus 5. You can write those separately, but I'm too lazy, so I'm gonna write x minus 5 squared. All right, oh, hopefully I left another, okay, good. Another page is open for me to write notes, that's good. All right, oh my gosh. This looks nuts, but it's kind of similar to the previous problem. We're kind of where we were in example, what was the previous example? Example 9? Where we started in the previous example. I think I said, I always write the first numerator and then the second numerator. Don't try to do anything interesting with it. Kind of keep it with the minus sign because I'm going to need to distribute that minus eventually. There we go. Okay, so that's all I did was take, you know, the numerators, 2x. Oh, what the heck? I just wrote it, and then the second numerator wrote it in the same fraction, that's all. Now they're sharing the same fraction. Isn't that cute? It's like, guys, we have the same denominator. Why are we separate fractions? We might as well get together and be friends. Aw, that's so sweet. All right. And at this point, the denominator is pretty much as simple as it gets. It's already factored. I can't really do much, but I guess the idea is this numerator, if I were to multiply this out, like here, x times x, x times 5, 4 times x, etc. There might be some like terms and I might be able to simplify it. So I think that's my job now, is to make it look pretty. Simplify the numerator. All right. 2x minus, okay. And I'm going to put this in parentheses because I know whatever the stuff that's highlighted in turquoise or blue or whatever color that is, all that stuff is supposed to get the minus sign. So I want to put that in parentheses. I'm going to multiply it out though. X times x is x squared. Or FOIL, I guess I could say, FOIL it out. X squared, and then x times negative 5 is negative 5x. Negative 4 times x is negative 4x. Negative 4 times negative 5 is positive 20. All right, I'm gonna be really careful. I know it feels like you could skip steps here and make it faster, but I'm afraid to make a mistake or forget to distribute. I'm just gonna keep that 2x the same, the minus the same, combine these like terms. That'd be x squared, and then I've got minus 5x minus 4x. Together that makes minus 9x. And then plus 20, there we are. Over, oh my gosh, this is a long problem. There we go, same thing. Whew. Now I can, now that the second parentheses or the second numerator is kind of simplified or whatever, I can distribute that minus. And that kind of, this 2x has kind of been waiting for the second numerator to simplify so he can maybe combine with any like terms there. But I have to distribute that minus first. The minus goes to the x squared. When the minus goes to the negative 9x, he becomes a plus 9x. And when the minus goes to the 20, he becomes minus 20 or negative 20, whatever you want to say. Take away 20, subtract 20. So many names for the same thing. The denominator has been the same for what, like 20 minutes now, it feels like. Okay. And now in the numerator, I see, if I want to write this in standard form, you know, from highest power to lowest power, negative x squared is the highest power. Then I have 2x and 9x together make 11x. And then that minus 20 is kind of all he's all by himself. All right, 2 over x, or sorry, 2 times x minus 5 squared. So this looks good. This is as simple as it gets as far as the subtraction goes, but I know it's like, there can't be a but. That took 20 minutes or half an hour to do that problem. Oh my gosh. Can this simplify now? Can this rational, this is a nice rational expression, but if I possibly factor the bottom, or sorry, factor the numerator, can it reduce? Simplify, question mark? Oh, so I need to try to factor the numerator. Or numerator. I'm gonna put a sad face because I'm bummed out that I have to do that. So this is one thing I should have maybe pointed out, or maybe there should have been an example like this in the previous page, but here we are. Better to learn a lesson late than never, right? If you're trying to factor a polynomial and the leading coefficient is negative, try to factor that negative out first. Factor a -1 out. If the leading, why am I writing this diagonally? I don't know. Coefficient is negative. I think that's a good way to go. Okay. Because so far that's, I mean, it would be a trinomial. So it looks like if that negative wasn't there, it would be an easy factoring technique. But that negative's kind of ruining it. So I'm going to take a negative out or a -1 out. You could just write a negative sign or a -1. That'll pretty much just change everyone's sign. The x squared becomes a positive x squared. The 11x becomes a minus, because that really this -1 is distributing in to make it a positive. And this -20, I factored out its negative. Now he's positive in here. And then blah, blah, same denominator for the last half hour. Okay. Oh my gosh. I feel like this is never going to end. But now let's see if what's in the parentheses in the numerator factors. If it does, this is the easy factoring technique because it's a trinomial with leading coefficient 1. Are there numbers that multiply to make 20 but add up to -11? Let's see, 20 can be 1 times 20, but there's no way I can make either of those numbers negative or positive and add up to 11. How about 2 times 10? That's close, but no, I don't think those can't add up to 11, or sorry, -11 no matter what. What about 3 doesn't go to 20, 4 goes into 20 5 times. No matter which of those 4 and 5, if I make both negative or one negative, it doesn't matter. That's not going to add up to 11 or -11. What else? That's about it, actually. So I think I did my best. You know, I said, you know what, maybe this simplifies, but it doesn't. So I could have just ended right here. Boom, 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 boom. Yeah, so this was just in case. What if I could make it look nicer? All those, I could, but now I know I could have ended there. Can't simplify. But I did my best, you know. I gave it the old college try, as they say, whatever that means. There, all right, beautiful. Oh, wait. If necessary. Oh, what the heck? Oh, man. There you go. They said the exact same thing as us. Okay. All right. Okay. I know this seems like a lot. This section is nuts. Oh my gosh, they throw so much at us. I feel like my brain's going to explode pretty soon here, but hang with me. There's only one more topic, and then I think we're done. Please tell me we're done. Yes. Whew. Now it's, oh my gosh, you probably won't see these again until calculus, and that's maybe one day of calculus. They'll say, remember complex rational expressions? And everyone's going to smile and nod, but really they don't remember. Nobody remembers what the, a year from now, no way anybody's remembering this, but maybe it'll be easier to relearn if you've seen it before. Complex rational expressions, also called complex fractions, have numerators and denominators containing one or more rational expressions. That doesn't make any sense, but they're just saying something like this in this example. It's like, you see there's a big division bar or a big fraction bar. Let's see. Here, right, there's a big old fraction bar, but within the numerator, there are a couple of little fractions. What kind of a sick mind thinks of stuff like this? Fractions within fractions? Why? Just tell me, why would you do that? Well, you might see them in calculus someday. So what do we do with those guys? What we want to do is make it so that there are no fractions within fractions. So I'm going to follow these steps up here. Let's see, we want to simplify it so that either numerator or denominator contains rational expressions. Okay, so the idea here is we're going to multiply the big numerator and the big denominator by the common denominator of all the little denominators. That sounds crazy. Multiply big numerator, and then by big, I mean just the numerator of the big overall fraction. Numerator, dang it, and big denominator by the least common denominator of all, that sounds crazy, little denominators. Okay, that sounds nuts, but so notice that this denominator, the denominator of the big overall complex rational expression, it's just a 7. There is no little denominator there. So the only contenders here are the denominator x plus 7 that's in the numerator, this guy here, and then this little x over here. We're just looking for the common denominator of those guys. This is just one factor. I can't factor that further. X plus 7 is prime. Same thing with x. So actually my LCD would just be, I need an x and I need an x plus 7 in any order. That would be it. I'm going to take that, multiply the numerator and the denominator of my big old complex fraction by it. And the idea is it should cancel with all the little denominators. It should make it so that there are no little denominators anymore. It's going to get rid of them. Let's see. Now, what the heck is going on here? Okay. I think I'm going to erase. There's too much stuff going on here. All right. All right. I'm going to go, it doesn't matter if you multiply on the left or the right side, but I guess usually when we distribute or multiply, we put something on the left side. I don't know. It doesn't really matter. But whatever you do to the numerator, you have to do to the denominator. Oops. That's 7. I shouldn't have put that x in parentheses. He doesn't need it. All right. So the numerator, we're going to have to distribute. I see this x times x plus 7 has to go onto this first term, which is a fraction, and onto the second term. In the big denominator, though, it's only that thing multiplied by 7, so that's not so bad. But I think what helps me is to write it out again, but with every term in the numerator and every term in the denominator given their own little LCD. So I'm going to rewrite that fraction, 1 over x plus 7, and then minus 1 over x. I'm going to separate them kind of far apart because I know each of them is going to have their own little LCD, x times x plus 7. Okay, we got x times x plus 7. I'm distributing him onto this first fraction, and then also he's going to be distributed onto the second fraction here with the minus in between. And then the 7 gets his own version of x times x plus 7. There we go. So that's kind of the idea. And then I'll simplify as I go here. Maybe just focusing on this fraction, 1 over x plus 7, what's going to happen to him? If I put that x, what's in orange there, x, the LCD, x times x plus 7 over 1, I get some cancellation that x plus 7 and that x plus 7 cancel. So this whole looks like a mess, but all that's left is x times 1 over 1, which is just x. But maybe I'll write x over 1 just to, to show my work, but that just ends up being an x. Okay, then I think something similar is going on with this fraction over here. I'm going to put that LCD x times x plus 7 over 1 and then cancel along the diagonal. I've got an x and an x will cancel. And all that's left really is the x plus 7 in the numerator times 1, which is x plus 7, over that 1. That's all that's left. And that'll just reduce down to something nice. And this, there's not much I can do with that. There was no denominator to cancel, so it'll just stay that way. 7x times x plus 7. Okay, and do I have, yeah, I have more room down here. That's good. I'm going to kind of rewrite it. Remember what we said, that a denominator of 1 doesn't really necessarily need to be there. So I'm just going to get rid of it. This will just become an x. And this will just become x plus 7. But I'm going to keep it in parentheses because I know this subtraction sign here is meant for everyone over here, not just the x in the front, but the 7 as well. And leave the denominator. There's not much we can do with that. Now I can't cancel anything yet. I have to simplify the numerator. I'm going to distribute this minus sign and then move it on down here. There was an x, now minus goes to the x, but the minus also goes to the 7. It was a positive 7, now it's a negative 7 over 7x times x plus 7. And that's interesting. The x is canceled because x minus x is 0. And all you're left with is that negative 7 over 7x times x plus 7. And this is why It was kind of good to keep the denominator factored that way. Yeah, because now I can see what cancels. If the numerator was more complicated, I would try to factor it, but all it is a -7. And I see the numerator and denominator are already factored. Numerator and denominator are factored fully. Obviously a -7 can't really be factored, so cancel any like factors. And I think that'll be it. So I see the 7s are in common, but don't forget the negative in the numerator. He was a -7, but now he's just a -1 because the 7 was canceled. And then in the denominator, you're left with x times x plus 7. That's it. Isn't that a beautiful thing? Whew, those are difficult, but if you remember the idea behind it, multiply the big numerator and big denominator by the least common denominator of all the little denominators, then you're going to be good to go.